Alright, day 18. So, as you see, I've really been slacking on a lot of these, and mostly because they looked super hard, and a lot of them are really hard. I did try day 16, and I have like 2 hours of footage for that, but it just did not work. So let's do day 18. Okay, thanks to your effort, the machine part factory is one of the first factories up and running since the lava fall came back. I've clearly missed a lot of lore. However, to catch up with a large backlog of parts requested, the factory will also need a large supply of lava. However, they aren't sure the lagoon... Yeah, lagoon will be big enough. They've asked you to take a look at the dig plan. R6 something, D5 something. The digger starts in a 1 meter cube hole in the ground. They then dig the specified number of meters up, down, left, right, clearing full 1 meter cubes as they go. Okay. Wait, what's this last part? The directions are given as seen above, from above. So if up were north, then right would be east, and so on. Each trench is also listed with the color that the edge of the trench should be painted. When viewed from above, the above example dig plan would result in the following loop of trench. Okay, so right, down, left, down, right. So you go right, 6, down, 5, left, 2, yeah, okay. At this point, the trench should contain 38 cubic meters of lava. However, this is just the edge of the lagoons. The next step is to dig out the interior. Yep. Okay, that's fine, I think. Contains a much more respectable 62 cubic meters of lava whilst the interior is dug out. The edge is also painted according. Okay, so I'm guessing part 2 is something to do with the edges, which makes me really glad because maybe I can just make a really big grid. And the thing I'm thinking of is that there's nothing saying that, like, you start at the top left, right? So we can't assume that. So yeah, like straight away left 7 on the inputs means that we're going to have to start in the middle. So how big do the numbers get? Not huge. So what I'm going to do is I'm going to make a maybe 10,000 by 10,000 array. Okay. And I'm going to start right in the middle. And I'm going to do stuff like that. And I think that will be okay. And then to figure out this stuff, I'm probably just going to count from the left to the right. I mean, that's going to be 10,000 by 10,000. Oh, it's fine. It's like Zig. It's really fast. Okay. A little brute force C, but no biggie. Okay, so let's start with an allocator. Heap.page allocator. I really should experiment with more of them. I might do in some future videos. Okay, so what I'm going to do is I'm going to do var grid equals allocator.alloc. I'm going to allocate, if I remember how to do this correctly, arrays of I guess because it's RGB color. So RGB color. So that's 4, 8. So 3 bytes. 3 bytes is 24 bits. So U32 should be okay to store that. An array of arrays of U32s, and the size. Let's make 10,000. Let's actually make grid size equals 10,000. Grid size, yep, and then for grid line for row, even 0 dot grid dot length, I grid at I is equal to allocator dot oh god, alloc. I think I need to do a try here as well. Okay, so alloc and you're just going to be U32s and grid size. Okay, zig run force main. Perfect, that's all fine. And we haven't copied this. You notice that actually took a little bit of time because it's allocating a lot of memory. Oh, look how nice it looks. Oh, yeah. Right. One thing I do have to do is initialize all of these to be 0. Init 0. Is there a method for that? Zig init int array as 0. Initializing arrays in 0 is 0. Let's see. Stand.memset, maybe? Might be right. Memset. This section sets all the elements of memory region to element. Okay, so grid I to be 0. Okay, that might be it. Okay. So what we do next is we take var x is equal to grid size over 2. We set that to y. And then we're going to take these about direction. Let's make an enum. I swear this is the 4th day or something. I make enums. Left. Well, direction is going to be down, right, up. I mean, you could probably go right and left straight away. I don't think the puzzle does that, but doesn't matter. Well, let's say direction equals direction up, and what we're going to do is for input line tokenizer equals stand.mem.tokenize sequence, and we're going to tokenize u8s. In line, we're going to look for the delimiter is a space, right? Space, this, or the brackets. Is that like a little something I need to do there? Not about the limiter actually. I can't really remember how this is used. While tokenizer.next let's just print s next. There we go. And I'm gonna yeah, I can leave those actually. Let's make you a U size. U size. Okay. I think we definitely do need to go on the spaces then. If we go on the spaces, and then yeah, we can get rid of the brackets. No problem. Bar direction equals tokenizer.next.question mark. Times, which is tokenizer.next stand.fmt.parseInt has to be tried. We're going to try to pass that as a U size. It's really overkill, but yeah, it's fine. As a U size. And then actually we're going to do a very similar thing for direction. Oh no, not direction. Color with the Queen's English there. And we're going to want to go 1 dot dot. Yeah, let's take bar string color equals tokenizer dot next dot question mark. Oh. String color 1 dot dot string color dot length -1, I believe, base 16, and we don't want to go from 1 because there's a hash. We're going to go from 2. String direction. There you go. So print color times, and then string. We don't need that one really. So our color is going to be color and times. It does take a little bit of time to ask half a gigabyte of RAM from the operating system. I think that's correct. Yeah, that's right. Great. Okay, so we've got those. Now, all right, let's continue. And what we're going to do is we're going to say after this for loop, we're going to go and say that for each one, right, for 0 dot dot times, we can discard that capture. We're going to color in the thing, right? We're going to go through each one of these. Okay, so I do need a little bit of clarification though. Like the top one is write 6 times, so 1, 2, 3, 4, 5, 6. So it doesn't count the one you start on. So it goes 1, 2, 3, 4, 5, 6, and then it goes down 1, 2, 3, 4, 5. So I'm not sure what happens. Maybe it's this one here. Left, left, up, up. Oh yeah, so yeah, you only start counting yeah, once you start to move, so right. 1, 2, 3, 4, 5, 6, yeah, for example. So up to times not inclusive. What we're going to do is we're going to say do we move then paint? Yeah, I think we do. We move. So switch guess I don't really need that enum anymore. Actually, switch on string direction. String direction 0 u, and what we're going to do is we don't really need this switch here, but I think the compiler must optimize it, right? Yeah, maybe, probably, that doesn't matter. We're going to move, so if we go up, we're going to do y minus equal 1, 2, 3. If it's down, plus, if it is right, we do x, plus, if it is left, we do x minus. Okay, so after that, we're going to go grid at yx equals to the string, the color. So we don't want to pass it as a U size, because otherwise that's going to be, it's not really going to work. We can also go U32, it's going to happen a couple times. So we're going to need direction. There we go. Does this run? Switch must handle all possible values. Oh, else unreachable. Okay, that runs. Great. And on this input, I guess just one thing we could do is if we see something like this, we start left and we're going to see empty space, so 0, 0. We see something. Yes. Okay. And then we continue. And then if we see something, we like switch a flag on until we see, you know, dots, dots, dots. So the dots inside are kind of like matter a lot. The only edge case would be when we're searching through rows like this. So I guess we could do like if this here is not a dot, we don't switch. Oh, but that's not. Well, this would be, you know, very nicely done by like floodfill or something. But that's, you know, don't really want to do that. Do I want to do that? Oh, I probably should do that, shouldn't I? Oh, that's just. Does it always make a loop? Like, is it guaranteed to make a loop? I mean, in this case it is, but I thought to say a dig plan, and I guess must be a loop. Oh yeah, if you fill it in, it has to make a loop, so you can have that guarantee. What is flood fill algorithms? All right, flood fill or flood fill. So it's like pretty straightforward. So we start inside. If node is not inside, return. So maybe flood fill is kind of what we need, but I think a BFS might be similar. So we start inside. So that might be a bit weird, actually, you know, starting inside. I mean, I could do it manually. Oh, can I? Can I even do it manually? I'm not entirely sure, actually, if I can do it manually. Yeah, I mean, I can for this particular example. I'll start with the example input and then figure out how I can get inside. So I think I could do a BFS, breadth first search, from the inside. We'll just do that flood fill, to be honest. Flood fill was super easy, right? Just go right, down, left and up. And then basically all I need to do is count. Yep, let's do that. Function count inside, that takes in a grid which is a pointer to an array of U32s. And an array of U32s. And also a pointer counter. No, I don't need to. I can return like a U size or something. Yeah. So what I'm going to do is I'm going to say X here is a U size and Y here is a U size. I guess I count 1. Counts current node. Or actually, current node if inside, right? If grid y x is bigger than 0, that is equal to 0, we are inside. So if it is not equal to 0, we return 0. And else, if the current tile, trying to just think this through, right? It's going to count everything around, and then what about the edges? No, they're going to work too, yeah. Else, we are inside, so we return 1 plus count inside. Actually, go on. Left equals count inside of the grid x minus 1 y, right, up, down, delete this, up minus y, this one, return 1, the current one we are on, and left plus right plus up plus down, maybe. And just to start off, print bar.1 is equal to count inside the pointer to grid. We're actually going to do grid size over 2 plus 1 for the x, because we just want to be there just to test this algorithm out. Grid size over 2 plus 1 for the y. Print part 1. There we go. Oh, just boundary error. I mean, it should stop recursion here. I guess it goes up, down, right, left, and from this example we would go up to the left, to down to the right. Yeah, this definitely prints a bunch of times, isn't it? Something y, I'm gonna do x, y. Yeah. Wait, that just kind of repeats itself. Oh, wait. We don't want to go to the left if we've counted it already. How do we do that? How do we, make sure we don't go back to the same one twice? We could assign grid to be 1. No, but that's just not great. How do we check? Yeah, maybe this is where BFS actually comes in better. Breadth first search. Okay, so we need a cube. Alright, I haven't implemented this in a long time. Grid, which is a pointer to the ESA2 array. Yep. And we stop searching if we are on a hash. Man, I'm struggling too much with this right now. I feel like I've done this before. I did this on the maze one, remember that? Or the pipes one. We just started from the left and counted. Yeah, but the pipes actually had like a meaning to them. Now we just have hashes. Not actually sure what to do here. Is there floodfill algorithm prevents going back to the same one? Question mark. Okay, maybe Wikipedia has one. And then this does it with a BFS. Ooh, this is exactly what I wanted actually. Span filling. Let's look at the animation. So it like keeps going up and then yeah. It's possible to optimize things by further. So start with a constant y, the first published good example of the following. Yeah, but this is inside. Yeah, inside function is the hard part, right? Yeah. How to figure out your inside a loop for flood fill. How do I flood fill unless let's count number of rows? Oh, this is interesting. I don't want to say too much. I don't want to say too much. Yeah, it is flood fill. I think we must just kind of keep where we are, surely. Old char, new char. Yeah, so I guess we could just let's go back to what we had. And should I keep a hash map of visited nodes during flood fill? God, that seems overkill. We could. Okay, wait. When we visit something, and that's something, we could set it to be like 1. There's not going to be a hex color with just 1. Well, there might, but the odds are like, you know, in our favor. I did make that mistake in day 3, but we set it to 1. And that's it actually. Okay, I think grid.star yx is equal to 1. And then if is smaller than or equal to 1, we return 0. That means we're in a node that has already been counted. And no, you just don't work. Oh, because right, yes. Oh wait, I have a trick. We mem set to 2, so that if it is 1, yes, good thinking. Yes, so what is going on here. What is this? So, yeah, it does a bunch of stuff. And it sets grid.star yx to be 1. And returns 1 plus whatever left, plus whatever right, plus whatever up and down. If grid.star oh wait, we only want to count 2's. If it is not, oh, that's basically what that is doing, right? If it is not equal to, we then set to 2. And to count inside, if the other part is equal to 1, or grid.star.yx. So if it is equal to 1, that means we've been there. Otherwise, if it's not 2. Otherwise, if it is not 2, that kind of makes sense in my head. Can be changed. Oh. No, that's probably like really weird logic. 24. That's incorrect. That's quite incorrect actually. So what did it check? It checked 5001, 5001, 5000, 5001. So I mean it starts here. Oh, it should go up and to the left, right? To find the little corners. Up and to the left. Top left, top right, bottom left, bottom right. The only thing is that if we are, oh no, seems like the loops are actually well made, so okay. Top left, top right, bottom left, plus 1, yeah, like this. Plus top left, plus top right, plus bottom left, plus bottom right. Still 24. Interesting. Print returning. Interesting to see what's going on. 5001, 5001. It goes to the left and returns. Goes to the right, doesn't return. That's good. It's like the furthest it reaches before returning. Before returning. God, it like does instant returns in a lot of places. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so it is it's not counting if grid dot star dot at y x is bigger than 2, return 1, return 0 otherwise. So when I reach the hashes, I still want to get myself the things. No, that's too much. Strictly bigger than 2. Let's get rid of that. So if grid is equal to 1, oh no, or it is bigger than 2, because 2 is what we started. So if it's bigger than 2, that means it's one of the colors that we found. What if we get rid of that? 58. I mean, it's closer, a lot closer, but does that make sense? Like, we start here, we go up, left, down, right, and then yeah, we'd never count that top left one. No, we definitely, I think we need this, but we're probably we're counting things twice for sure. Yeah, we're definitely counting things twice. Yeah, I've never. Let's just the x and y's again. X, y. Oh, and of course, yeah, new line. Let's just a little bit of checking ourselves an AOC puzzle without this. Okay. 1 1 1 1. We count that, and actually we want to say print counting current, print not counting but still returning, so we can actually examine what's going on. Okay, that's great. 1 1, and it goes 0 1. That's to the left. All right, counts the current. It goes 2 1, and then it goes back to 1 1. It doesn't count. It goes 3 1, goes left, doesn't count. 4 1, goes left, doesn't count, goes right. Yep, doesn't count. 6 5 counts the current. 5 0 up. Basically, I'm looking for repeats, I suppose. I'm looking for stuff that is repeated. Yeah, but like 5 3 3, 5 5 0 0 3, 5 0 0 3. Oh, I know what it is. I know what it is. It's not repeats in the tiles, but it is repeats here. Maybe. And maybe I'm off by 1 now. No, whoa, that's too much. Still too much. but I think maybe more correct. Am I repeating anything? Minus, plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus. Yep. That's all good. Strange. Gonna have to go back here then. Seems to stay like quite stuck in those lower parts. We have 9 there, 4. So this is 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I mean, it seems to reach them all. But yeah, counting too much. Count too much. Think of 1 plus. How many am I off by? I'm off by quite a bit, so. Why am I off by quite a bit? Setting the y x equals to 1. So it doesn't get counted again. So if it is equal to 1, let's split this up just because it just looks bad. If it is bigger than 2, we're not in the inside, right? Because the inside has to be 2. And we take away this, not counting count, because this will be a hash. We set the current one to this, to be 1, so it returns 0 on next subsequent calls. Then we check, and we add them all up. Well, I mean, I don't think there's that much to do except continue. So I'm gonna do a minus like 4995, just because, you know, make it easier to see. Did I count this powder? I'm tempted to not record this part because it's just gonna take, you know, a little bit of time. To figure out. Yeah. Did that do anything, by the way? Changing the F statements? No. Yeah, I thought not. Be weird if it did. So it starts 6, 6, 5, 6 counts, 7, 6, tries to go back to 6, 6. Let's not print the not counting ones. Let's only print here, not there, to check the ones we are counting. Might be a good idea. So we're counting 5, 6. Yeah, and then I thought I was off by 1 as well. 5, 6 is here. 11, 6. So no, that's x. 5, 6. This one, and then 11. So 5, 5, 6, 7, 8, 9, 10. I think then this is 5, 6, 7, 8, 9, 10. Ooh, counts 11. Maybe it's nothing to do with my floodfill, and it's something to do with, you know, me being bad at engineering. Oh, come on, man. I thought this was going to be like a fairly straightforward one. Let's comment these bits out, and let's do 4, 4, in this case 995 dot what should we say, 5050 I. That's going to be our offset, and we're going to do the same here. Because remember, we're kind of plumping this in the middle of a big grid. If grid at j, no, I is row j is equal to 2, smaller than or equal to 2, let's say, we're going to print a dot with nothing else. We're going to print a hash. Here we're going to print a new line. Very nice and easy visualization. There we go. That works really well. Here we go. And then is equal to true, otherwise we print that. Let's do this, and now let's print again. Maybe I shouldn't do the counting there, because now that's just worked perfectly. Yeah, you know what, I'm gonna screw the counting. Screw the counting, let's just do this a bunch of times. And then do part 1, p size is 0. And I mean, we're going to print just because it looks nice, but if it is a hash, we're going to do part 1 is equal. So it was right, but maybe, you know, separation of concerns there a little bit. What? What's this? Oh, just return then. I'll return void. There we go. Okay, we spent maybe too long on that. 62 is correct, I'm pretty sure. Yeah, so the thing is that we're not super deterministic with it. We're really not deterministic with it at all. So here, actually, I'm not going to count inside, and I'm going to have to do like some bigger ones. Can I print 1,000 characters on the screen? No, that would look too weird. Alright, let's try this. Let's size you up and really zoom you out. Oh, that was not enough zoom out. But, hey, look at that, that's kind of cool. I think, oh, Jesus. We can go 8 there, replace it with 8. Wow, crazy. It's just minuscule. And I mean, yeah, we're gonna have to just, wow, that looks so cool. Find a point, just kind of at random. I don't really know the best. I think maybe just a good way of doing this, but not completely deterministic, just the best possible, is to go right down the middle, find out. You know what? I don't like. Does not matter. Does not matter. Let me just, you know, leave those out. I wonder what happens if I do that. Like actually leave it just as +1, +1. Goes left, up, left, up, left, up, left, up. Down, right. Yeah, I mean 49061. That actually looks correct. Yeah. Okay, right. You just gotta do what you gotta do sometimes. The elves were right to be concerned. The planned lagoon would be too small. After a few minutes, someone realized what happened. Someone swapped the color and instruction parameters when producing the dig plans. They don't have time to fix the bug. One of them asks if you can extract the correct instruction from the hexadecimal codes. Each hex code is 6 digits long. The first 5 encode the distance in meters as a 5 digit. The last one encodes direction to 0, mean R, 1 means something. Yeah. So basically, they're saying make a much bigger grid. So my current grid, let's do some napkin maths, is 10,000. 2, 3, 10,000 times 10,000. And how many bytes? That's a U32. But for part 2, we could shrink it a lot. We could shrink it to 1 byte. Times 4. How many zeros is that? 1, 3, 1, 2, 3, 1, 2, 3. 4. Yeah, that's a lot of memory. So I'm basically going to explode my CPU doing this, right? If I do it this way. Well, actually not my CPU, my memory. If I do 100,000 even, and then what are the coordinates that they were looking for? Like, I need to support 1,000,000. So, and 1,000,000 would mean like starting at 2,000,000. So 2,000,000 times 2,000,000. And let's just say I can get it down to 1 byte. How many is that? Like underscore this here. So kilobytes, megabytes, 4 terabytes of RAM. Yeah, that ain't it. Is it? No. Right, kilobytes, bytes, no, yeah. This would be gigabytes. That would be doable, but no. So now that's just, wow. Yeah, oh god. We would need to store the visited coordinates in like a map or something. Yeah, we need to store them in some sort of map. Oh, instead of floodfill, is there a generic algorithm for area? For area of shape, for area of shape with straight line equations. Is there a generic function to find the area of any shape? Lebesgue measure. If you mean arbitrary self-explained probabilities, no, unless you regard definition of this. However, you write about in order which they are connected, that makes me suspect they have a sequence of points between as compounds of the boundary. In that case, maybe the shoelace formula. Okay, promising. Planar, simple polymoid with a positive oriented clockwise sequence of points. Yep. Okay, I can definitely do this. For the simplicity of formula, let's say P0, the formula is the area of the given polygon can be expressed by a variety of formulas which are connected by simple operations. The trapezoid formula sums up a sequence of oriented areas. So, yep. So exactly, because it creates little, these little trapezoids. The sum between n, which n is the number of points, I believe. I think shoelace is what I want. Is this correct? Trapezoid, the edges determine the trapezoid in case lengthwise. Okay, so the shoelace formula is we need to calculate some 2D. Oh, it's been a while since I've done that. 2D determinants by hand. A, B, C, D. I'm just remembering. So it's BC minus AD, if I'm not wrong. So we take. Oh, it's not just 2D. Or I guess, I mean, it is, but. Okay, so. Right. I think this is okay. So 2 area is the first point and y of the second point, x2, y2, x2, y2, x3, x3. So it kind of chains in like a shoelace. Yeah. Other formulas. What is this? This looks a lot nicer. I'm gonna have a look. Versus shoelace. Is there anything? I mean, this is the shoelace, also known as Gauss formula. So the formula is mathematical algorithm for the simple polygon. Yep. Oriented parts and one of its 4 edges. I mean, I see no reason why this here doesn't work, right? This actually looks a little bit nicer. The area is equal to half of the sum of those points there. So we could take a bunch of points where we are. So, you know, I'm going to leave part 1 as is, like this. Going to take part 1, but you know, I'm going to do this next one now. So next we need to figure out. Okay, the direction is encoded there, so we need to take away. We need to see if it mods by something. Okay, we'll leave that there, you know, part 1. But we go. If color mod 0 equals 0, no, mod 1 equals 0. So no, mod, not mod 1, right? If color and 1 equals 1. Yes, something like that. So if it is 1, 1 means down. So I'm actually going to print down because I'm not sure if I trust my maths all the way there. Color and 2 is equal to 2. Alright, so then 2 means left, and I guess 3 means right, and the other means otherwise up. Great, and print S, which is the line. Great. Right. So will be right. No, 0 means right. Wait, 0 means right. 1 means down. 2 means left. 3 means up. Okay. Right, down. Right. 0, which is right, down, right. What the hell, man? Wow, this is not the hard part, but yet. Two. What? Yeah, I'm actually gonna take away 2 here and then just take out the very last one. That's just gonna be easier, you know. So 461,937. Yeah, that's right. And then we go from part to direction, which is equal to string color of string color dot length. Oh, my LSP stopped working. Why is that? Has it stopped working? Seems like it has. Where's that? Length -1 dot dot and then 0. Part 2 direction. Length minus to the length, maybe -1 and -2 there, yeah, to get that second to last character. Yeah. Take away the ASCII 0. Yep. If part 2 directions equal to 0, as if part 2 directions equal to 1. Find 1. Yeah, that's it. And okay, if this, then what we're going to do is we're not going to take where we are currently. We would normally increase it. We're going to take the if it is 0, which means, what does it mean? Right, we're going to say back with an interruption there, but alright, 1 means down, and 2 means left, then this one means up, 3 means up, right? Yeah, right, down, left, up. Okay. So we're going to take x plus, we're going to go to the right, we're going to say, oh, we need a map. Well, coordinates, yep, equals standard dot auto hash map between u-sizes, no, u128, we're going to do a shift, we're going to shift the x to the left or something, and just boolean or something, that's it, dot init allocator, and we'll leak memory, no need to free. So about C1 is equal to as u28 x, so we're going to do x plus 1, it's going to go to the right, it's going to shift over x plus 1, maybe shift it over 64 times, and, no, ORed with as u 128 of y. Chords dot put C1 true or something like that, yeah. And then it's also going to say, we're also going to say that, wait, hold on. If we are here, we go to the right once. We set this one, so 1, 2, 3, 4, 5, 6. Yeah, so we do C2 is equal to x plus, not par2 direction, but the color, which is not really a color, but yes. C2. If we go down, I'll do that in a sec. We'll do this left one first because it's a little bit easier. -1, I'm just going to go, instead of plus, we're going to do takeaways, and a minus there as well. If we go down, we leave xb, +1, x plus color +1. Okay, so if we go up, we take away instead. Okay. Cool, so just for part 2, I want to figure out the number of vertices, which is equal to, well, it's going to be the same as in the example. It's going to be the number of vertices, which should be the number of inputs as well, but yeah. Chords dot count print vertices, none of vertices. Is there any print statements anywhere that I don't need? There is this one. There's an integer overflow. That makes sense actually. We don't really need x, y there. Oh, and we need to set it. Oh, right. Up to x is ooh. Yeah, so we're gonna need this is gonna need to be an I, because we can have negatives. Oh, do we? No, we don't. You know what? Let's not do negatives. I don't want to. Let's just make this a U size. Let's set it to 220 million. Because I can still store really big values after that. And I can just ignore basically all of that. X goes to part 2x. Oh. Y goes to part 2y. No, can't do that. Part 2y, part 2y. Part 2y. Okay, and the thing is, what I forgot to do is we have to say, after we've done that, we have to say part 2x is equal to part 2x plus color plus 1. And if we're going down, we say part 2y is equal to part 2y plus color plus 1. And part 2x equals part 2x minus color minus 1. And this is part 2y, it's part 2y minus color minus 1. And I think 20 million might be cutting it short. Let's go a much bigger number. This is a U size, so it should hold a lot. 20 billion versus 28. Let's check. So 1, 2, 3, 4, oh no, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No, it should be the same. Oh, I don't want to put it twice. I only want to put where it ends. Yeah, I think I'm pretty sure I don't need that. This first one. 28, that was double what it needed, right? Now I'm at 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Perfect. Perfect. Now, to implement that, the shoelace formula, which is this. The trapezoid formula sums up. Yeah, so we go through all the points. That shouldn't be too bad, right? I mean, but it is inclusive, so I'm not sure. Also, it is a huge number, right? Did you see that? Yeah, massive. Okay, I'm just gonna do it. I'm just gonna do it in line as well. It's easier. We can get rid of this for chords dot value iterator or value iter equals chords dot key iterator, while value iterator dot next value. No, it says a key. Keys key dot star plus c equals, we're gonna have to take x. X I think probably conflicts with that, yes. x, my x, let's say, no, my x sounds weird, x, x1, why not? We have to take the key star, we're gonna have to shift it to the right 64 times to get that. And then for y1 we need key, and we need to AND that with 0x, so f is 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 60, 64. Really just big number there. So we take the current one, and what do we do? R2 plus or equal to yi plus 1. Oh, okay. Oh, we're gonna need to iterate over it then. Like, we need to find the next one. Yeah, of course we do. Is there a way? There probably is, like, chords dots to, no, can't put value in it, dot get, move. What we could do is we could do the previous instead. Prev value. Or is there a keys dot items? Is that actually items? Just comment that out. Print length or something of keys dot items dot star dot length. Index syntax required for unknown unknown length, right? Yeah. Okay, so we do var prev equals keys dot next dot question mark, and we go through the next one. These are actually the next ones, so var x1, x1, y1, and this is not key, this is prev dot star, previous dot star, and here we're going to say previous is equal to key. We're going to get to the last one. Yeah, this is fine. So we're going to take y I plus, so we're going to do y2, y1 plus y2 times xi, which is x1, minus x2. We're going to times those together. But what about negatives and stuff? This is assuming, maybe it's not, maybe negative various part of it, right? Subtract some stuff. You want to write integer I 256. how do I do this again? Can I do as I256 as I256? Does that work? As well. Yeah, let's just do this, and now we can just do stuff normally, hopefully. Great, so we get a very negative value. Did I get these the wrong way around? I mean, it doesn't matter, it's still gonna get, oh no, I get a positive one though. That's still wrong. Still like quite wrong. Yeah, I'm gonna think about that for a bit. I think maybe we implement the shoelace instead then, where we do the same thing. And then, right at the very end, we need to do one extra matrix there. So, the discriminant of a 2D matrix is equal to AD minus BC. Yep. So, in this case, we need to do x1 times x2. We need to do x1, y2 times y2, take away x1, no, x2 times y1, and then at the very end we need to do keys equals chords dot key iterator again, for first equals keys dot next dot star, we're going to say var first equals keys dot next dot question mark, and then previous is equal to first, and previous change about first stays. So then what we do is var2 plus or equal to let's take these from here, previous, the previous, first, the first. So actually, no, those first ones, which is y1, they should be, it should be the other way around. First, priv, and let's copy this, and that gives us 2 equals divided by or equal to 2. Alright, what do we get? Division with signed integers must use div trunc, div float, div extract. Oh, okay. Div trunc, but 2 and 2. Is that better? Oh man, why is that so bad? That's so negative. Okay. And x1, y1. I mean, they all look like they're fine, you know? Yeah, I mean, they all look okay. But why do I get some negatives. Shoelace formula gives negative answer. Oh, oriented areas. Oh no. There needs to be in like order. So it can't be a map. Needs to be an array list. Yeah, I mean actually array list makes a lot more sense. I don't know why I did a map. Array list. There we go. For chords dot items dot items, then we have a key. Actually, it's just going to be key and then previous. First is equal to chords dot item 0, and there we are. Maybe that works better. Try chords dot put c2 to be try chords dot append c2. Yep. Oh, that's right. Yes. Now it goes clockwise. Gives the right answer. Gives us nearly the right answer. We're off by not much, but we are off. 952 408. So it makes it look like we're not quite you know, our calculations with the plus ones and stuff like that might have been wrong. Okay. Yeah, so I must be an off by 1 error because we are really, really close. So we took the last vertex, and we're gonna go. What if we don't add ones? Like at all? Because maybe with this new like mathematical format we don't need to, but our answer is bigger. Let's see. That's not correct. 953 408. Is that closer or further away? 409. 9 was closer. Interesting. Yeah, we're so close to an answer there. Yeah, that's annoyingly close. Truncate division rounds towards 0 for unsigned integers. I wonder if this makes any difference, what we do. Exact division produces a remainder. Yeah, I guess it shouldn't really. 3 times this by 2, you would get a. Wait, really? Produces a remainder, are you sure? If we print part 2 up there, we wouldn't get a remainder. Oh, a 3. And it just kind of ignores that. Okay, I mean, I guess it's fine, because we're off by so much, that probably doesn't matter too much. Is it like a scale fact thing? I should go like 0.5 or something? I'm curious, because I could do color times equals 2, and over here divide by 4. No, the area is going to be, yeah, 4, I think 4 is correct. Or 8, it might be 8, so I divide by, yeah, it's 8. It's funny that gives me a different answer. Oh, man. It was going so well. It's like so close, so close, so close. Alright, I'm gonna just stop for a second, think about it. Alright, so that didn't actually take too long. I look at Pick's theorem, and this isn't what I did, but it looked promising. And the fact I was off by so little, I just experimented. And what I did is I counted the part 2 edges. That is, basically every time you go along, right, up, down, left, I counted. However many that would add to the edge, the perimeter. And adding the entire perimeter would give me too much. Not adding it would give me too little. So I divided by 2. And when you divide by 2, I'm at 114. And if I add the 1, I'm at 115. You know, it's kind of weird, but look, if it works. If it works, it works. Let's see what we get. Part 2. Alright. Let's hope we're right. Alright, cool. So, alright, I learned something new today. Actually, the shoelace formula for grids needs to have the perimeter halved and n plus 1. Because it only measures the very inside, right? It doesn't count the perimeter, nor should it, right? Cool. Pretty cool. Yeah, thank you for watching. Hopefully see you tomorrow, but I don't make any promises. But yeah, alright, take care, bye.